Hello guys, back with another power electronics video, and today is going to be a special one because it's complex topology. It's, as you can see, looking at the circuit, we're looking at the PFC, power factor correction, and particularly the boost power factor correction as they call it. So basically, just to give you a background of why we need power factor correction, just go into this reference manual of an XP. It's good. So basically here they show, right, this is our standard power supply circuit, that you take your AC input, pass it through a bridge rectifier, and you have a large bulk capacitor here, generally in multiple thousands of microfarads, to keep the ripple low, and after that you put it to your load or whatever, right? So while this is classical and it works and it's good and it's still used today, the problem is, if you look at the current, the voltage, we all know it's this sawtooth looking output, right? That will be across your load. And the more you increase your capacitance, this ripple will reduce and you'll get almost a constant DC voltage, which is good. But if you look at the current, as they are shown here, this thin black line is the voltage, right? Rectified voltage. But if you see the current, it only, there are these sharp peaks, which basically happen because the current is only drawn when the capacitor voltage drops below the peak of the rectified voltage. So that's why you get these really peaky currents. And if you try to find the power factor of this, which is basically dependent on both the voltage and current, right? So the power factor is generally really bad. It's almost generally zero point 0.6, zero point 0.7. So basically you draw more current and it's not useful current. So you need to make your wires thicker, and overall the efficiency reduces. So that's why you need power factor correction. And this is generally, it's compulsory above 75 watts, as they have shown here. There are regulations for this. So if you look at your phone charger or something, generally it will not have power factor correction because they're generally much below that. Of course, these days you have high power chargers, but if you, let's say, a standard 25-30 watt phone charger, it definitely doesn't have power factor correction because the cost simply wouldn't justify it, because you need specialized components for this. So that just has this same classical circuit, but again, of course, they use flyback converters or forward converters, but that's for another day. Just looking at power factor correction, now that we know that we need power factor correction, one of the common topologies is this boost PFC or classic boost PFC. So what they do is they keep the input part same, they keep the bridge rectifier the same, but instead of putting this bulk capacitor here, because that's the problem, that is what draws those sudden currents, they put a boost converter in between basically. So if I just go into this circuit here, it's better. There's our, if you just, this part we know, right? And this capacitor is just a smoothing capacitor, it's not your bulk capacitor. So just keeping this aside, if you look the circuit this onwards, you have the series inductor, a low side switch, your diode, and then you put the bulk capacitor. This is basically our boost converter if you just look at it. So if you just combine this bridge rectifier with a boost converter, you can do the boost PFC. And what you basically want to do here is, you want to bring your input current in phase with the input voltage and sort of track that waveform. So if the input voltage and the input current are in phase, you can say that your power factor is very good, and sometimes even reach unity power factor. Of course, that's, there are a number of things that go behind it, but in theory, yes, you can reach unity power factor and get the best efficiency. So again, in general, in like how there are in any power converters involving inductors, there are three modes: the critical, discontinuous, and CCM. So I'll be looking at CCM because that generally has the best efficiency, though it is more complex to control. And as you can see, what we basically want to do here is, this inductor is there, right? The inductor, what we basically want to do is, we want to shape this current to follow the input voltage, rectified input voltage to be precise. And if we do that, basically we can, yeah, bring the power factor better. And in critical conduction mode, the inductor current never drops to zero, so you want to continuously track this input voltage, of course with a ripple depending on your switching frequency. And yeah, that's what you basically want to do. And for this, basically you need to measure three things. And if I just I'll go into the control theory a bit later, but what you want are three things: your output voltage, because you have to maintain that output voltage at a stable bus, Then what you want to do is measure that this rectified input voltage, because that is what is going to shape your reference current. And the third thing is you need the current itself, because you need to know what current is flowing at that instant period of time. So you need two voltages in one current. So for the voltage, output voltage, what you can do is you can just use a resistor divider generally, and yeah, send it over to the ADC. And of course it goes without saying that I'm doing this on the microcontroller. There are many discrete ICs available out there for doing this, but yeah, I'm going to be designing the control loop myself, so everything is going to be on the microcontroller, the STM32. So you need the output voltage, so a resistor divider works there. And even this input rectified voltage, since it's DC, as you can see, again you can use a resistor divider and get that too. Only the current is a bit of a headache. You basically have to, either use some kind of Hall effect sensor, which is what I have used, or you have to use a shunt. So shunt and measure the drop across it, and that becomes voltage again. So I tried the shunt, but it didn't really work out. But the Hall effect one, this is a very popular one. You might have seen this. The ACS 712 is this small module that comes. If I just show you, it's this kind. And they come in 5 amp, 20 amp, and I think 30 amp versions too. So they're very good. They're Hall effect based. The only demerit of them is, and another good thing before I list the demerits, it's also isolated. So currently my microcontroller ground is common with my power ground, because I'm doing it on a lower voltage. I'm not doing it on the 400 volt bus or something, since I just want to prove the circuit. So if you do have those lethal high voltages, isolation is always good. So this sensor is good for that. But now just going into the negative part of it, as you can see, this particular module, it has only a 80 kilohertz bandwidth, and it does have a rise time of 5 microsecond. That means if you're switching at a high frequency, like how I'm going to be doing, same as these reference manual states, I'm also going to be doing 100 kilohertz switching frequency. This actually can't track that current that fast enough, because it just doesn't have the juice to track it. But in our case, it might actually be a bit advantageous for us, because anyway we want to track the average current, right? We don't really care about that ripple. We're not doing peak current mode control, we're doing average current mode control. So we just want that average current. So the average current will, that ripple will anyway get filtered out, you can say, sort of, because this sensor just isn't fast enough, and that might be advantageous for us. So I've still used this, and it seems to be working fine. I just had to calibrate the sensor a bit. The output voltage wasn't exactly according to the data sheet, as it said 185 millivolt. But yeah, keeping that aside, let's just go into the control part of it now. I have designed it in MATLAB first, Simulink. It's very good for this. So I have the entire circuit in Simscape over here, blue color. And this is the control part of it basically. And I'll just go into it roughly. What you basically want to do is there are going to be two loops. There's going to be a outer voltage loop and an inner current loop. This voltage loop is going to be slow, since your load changes are generally slow. You don't really have to keep sampling way so fast and change that. That'll just be a waste of computation. So your output voltage loop is going to be slow, and your inner current loop has to be fast, and generally as fast as you're switching, because you want to immediately change the course of the current depending on the input voltage, right? So that's why this has to be fast. So what you would do first is you find your output voltage error depending on what you want your bus to be and what it actually is. Then you pass it through a PI controller, and that PI controller basically forms a current. So you have a voltage error here that transforms into a current of sorts, and to give it the shape, you take your rectified input voltage and you normalize it between 0 and 1. So you just divide it by the peak of the voltage, and once you do that, you multiply both of these together. So this sort of forms a rectified sine wave, and it tells you how much current is needed. So let's say if there's a large error, this is going to be a large amplitude sine, whereas if the error is small, it's going to be low. So that is our current reference basically. Like how we had our voltage reference here, we basically hard code it depending on what we want. This is dynamically changed depending on how much current is needed. So that forms the current reference, and then you get your actual current from your current sensor, and you minus it again, finding the current error here. Then once you get the current error, again you have to pass it through one more PI controller, and that ultimately is compared with the carrier, and yeah, you form the PWM. and that PWM is essentially fed to this uh, MOSFET, because that's our only active switch here. So basically what you're going to be doing is, at the peak of the sine, the voltage is going to be maximum, so you don't really need much current. So it's the duty cycle is what you control, it's going to be low, whereas near the, as you go towards the zero crossings, you need more duty cycle to maintain the same voltage. So yeah, that's how the duty cycle keeps changing depending on which part of the cycle the sine is in. And if I just the PI tuning does take some time. I won't really go into that, but if I just show you the simulation results, you can see here that yeah, you can see here that my output voltage, since I in this simulation I want it to be at 50 volts, it's sort of, with the minusing the ripple, it sort of stays stable at 50 volts. And if you see this yellow sign, that's our input voltage, and the blue, that's our input current. You can see how they are in phase, right? And that's exactly what we want with perfect correction. My And if you just forget this zero crossing part, which will always be there, it's in phase, as you can see basically, and that's exactly what we want. So that's the simulation of it. Now I'll go into the code, and everything is on the STM32. I won't really go too much into the code because it does take it'll take a lot of time to explain it, and I don't want these videos to be too long. So I've just, everything is in C, and I've used a lot of define preprocessor directives and all of that, many variables, much more than normal. And yeah, everything runs in the while one loop. I have two timers. One timer is for the PWM itself, and that also triggers my inductor current ADC. And basically it uses DMA, direct memory access. Maybe that's a video for another day, but basically it takes the load off the CPU. The CPU doesn't have to work as hard. And my other timer basically runs at 10 kilohertz. That's for the output voltage and input voltage. As I said, you don't really need to keep sampling the voltage, it's not going to change so fast. So we have those two timers, and they use DMA, and they directly transfer the value which is detected from the ADC into the memory. And yeah, in the actual while one loop is where I handle all the control logic. So I won't really go too much into the code. Let's just go into the hardware, and I'll show you how the whole circuit is laid out. So yeah, this is the hardware, and there's the STM board, the Nucleo, and that's the gate driver IR2110, and there's the actual power circuit, the MOSFET, diode, and all of that. And a couple of these resistors over here are basically just the resistor dividers. And over here I have a op amp. I was actually going to be using this for the current shunt, but I switched to the ACS module, so I didn't really need it, but I just kept it, and I'm sort of just using it as a buffer for the ADC. You don't really need it, but yeah, nevertheless I have that there. It's the MCP 6004. It's a rail to rail op amp. And there's the inductor toroidal core. I generally, for the PFC, they often wind the inductors themselves. I haven't really got into that. This is just a off the shelf one, but maybe I'll look into the magnetic design someday. And there's the output capacitor 2200 microfarad, and there's the load 100 ohm power resistor 10 watt. And for the input, this is the bridge rectifier, just four Schottky diodes, and these can only handle 1 amp, so actually they're not really made for high current per se, but for just showing you this 100 ohm load, it should be more than enough. And our AC input, as I said, I'm not doing actual mains. I've just stepped down the mains with this step down transformer. It's a 12 so yeah, 12 volts AC input through the bridge rectifier. And to just show you, I'll show you three things. We have one oscilloscope here set up for looking at the gate waveform, and there's the multimeter for looking at the output voltage, and another main oscilloscope here for looking at the actual inductor current. So I'll just power this up, and yeah, you can see, I'll just show you all of the waveforms. And yeah, I'll just turn this on over here, and you can see we're roughly at a DC bus of 18.3 volts, and the ACS is on, and here is the current. The trigger is, it hasn't triggered properly, but if I just stop it for a second, you can see minusing the switching spikes, yeah, something like this, you can see that the current is in sinusoidal, right? This is much different from the peaky currents that would have been there in case of the normal bridge rectifier. And yeah, it's the period is, even though it doesn't show it correctly over here, it's due to all these switching spikes, but it's 50 hertz. I'll show it to you in a minute. But yeah, you can see this is the inductor current. I've just placed the shunt there to measure the current across it. And the duty cycle, if you see here, it's I have capped the maximum duty at 80%, but basically it will keep changing it. You may not be able to see it very well right now, but yeah, you can see that it's changing depending on how much juice it needs. And yeah, there's the load and the two waveforms, right? And actually, just to show you how the input voltage is in phase, I had put another probe before over here. I just removed it, but I have taken a picture of it. I'll show it to you. And yeah, this was the picture which I took on the same oscilloscope. You can see this was the yellow is the inductor current, and the blue is the input voltage. And minusing all the spikes, you can basically see, right, how they are exactly in phase. And the duty cycle dynamically changed depending on how much voltage was there. Yeah, the duty cycle changed, and the input current drawn from the supply became sinusoidal-ish, sort of. Of course, this can be improved. Can improve my gains a bit, but definitely it's in phase. I can say that much. Another thing is the output voltage. I can show you that the output voltage will inherently have a ripple at your rectified, which is 100 hertz frequency, right? After you rectify. So I had my scope here in AC coupling because it's very small. Generally, you saw that it was at 18.5 volts, right? So that will roughly remain stable because that's what your outer loop is for. But if I just AC couple it, you can see that the peak ripple is at 100 hertz, but it's very small. As you can see, it's just peak is what, roughly 150 millivolt, right? So it's 300 millivolt peak to peak, which is very low. And yeah, that's primarily because of this giant capacitor I have here, 22 microfarad. If you reduce this again, yeah, this ripple will increase. But yeah, that was the whole PFC circuit. And this was one of the more challenging circuits I've done till date. The control loop did take a lot of time to tune, but it's AC to DC, right? It's one of the most important ones because we want DC for so many of our applications, and especially in industrial ones, right? Motor drives and all. This is used a lot as the active front end, as they call it, to get the stable DC bus, and then later you have the inverter and all of that. So yeah, that was today's video on Boost PFCs. I hope you liked it. I did try to keep it short, but it's already, I think, what, 17 minutes or something. But yeah, I hope you liked the whole hardware. And yeah, it goes without saying that since this was low voltage, it's okay, sort of, that I did on the breadboard. But yeah, definitely a PCB will get, maybe even reduce these spikes a bit, because this noise is all over the place. As you can see, there's an inductor here. There's the uh, a lot of stray wires going everywhere, so it's a wonder that it worked. But yeah, and also, if you can see, the DC bus, you can depends on how much you can, your transformer can also supply, right? Because even though these transformers, they do say 3 amps and all of that, often it's not really true. Because if you see, the core is physically small, so it can't really pump that much current. The voltage sags when you draw a lot of current. So if you have one of those giant transformers, it can probably act as a stiff source and yeah, improve the performance. But yeah, that was the whole circuit. I hope you liked it, and yeah, stay tuned for some more videos. Thank you.